Hi and welcome to Geeks for Geeks. Today we would be discussing the problem kth common ancestor. So in this problem you are given a binary search tree like this and you are asked to find the kth common ancestor. Okay. So let's say that it is told to find the second one, okay, of 4 and 7, second common ancestor. Second common ancestor is none other than 3 itself. Okay, so now the question is asking me to find the kth common ancestor. So there is a property, or I can say a small observation, that is existing out there. So just a quick heads up before this. If you are a person who is not really acquainted to the world of common ancestor, that is lowest common ancestor. So by the way, this question is nothing but an extension of lowest common ancestor. So there are two different domains of lowest common ancestor. The very first one is lowest common ancestor in a binary tree. The next one is lowest common ancestor in a binary search tree. These are two different dimensions. And in the era of lowest common ancestor in a binary search tree, this problem is just an extension of it. Okay, like lowest, here it is asked kth. Okay. So a small bit of observation that needs to be emphasized is, so let's say we have something like this. Okay, let's say this is a binary search tree and we are asked about the common ancestor. Okay, let's say the common ancestor of 6 and 13. Here let's say somewhere upwards also. Here something, let's say a value x is there. So if I am asked a value, like if I am asked the second common ancestor, then I would first go to this common ancestor and then the counting would start, that this is the lowest common ancestor, this is the second lowest common ancestor, this would be a third lowest common ancestor. Okay, like if we want, like what I meant to say is, if let's say this is me and this is my sister, on top of us we have our parents, on top of ourselves we have our grandparents. So the counting would start from here. Okay, the counting would start from here and then go here. Like a better example would be, to make it understand more, let's say my sister has a son. Okay, my sister has a son named as Ashu. By the way, this is my pet name. Okay, so let's say if it is asked the second common ancestor of me and Ashu. So the counting won't start from my sister. The counting would start from my parent because it is the first common ancestor. Then it would be the second common ancestor. Then it would go on. Okay, so the clear observation is that the counting of 1 to the kth common ancestor would start from common ancestors only. It won't start from my sister. Okay, so clear observation would be that we need to find the lowest common ancestor and then find all the ancestors and then report the kth ancestor. Then report the kth ancestor. This is what I meant to say. the counting. Why this thing would strike me, that lowest common ancestor? Because of this thing, this idea. Okay. Now the problem is that finding out the path is the second problem, like the second subtask of this. The very first subtask is to find the lowest common ancestor. Now our problem statement is find lowest common LCA of binary search tree. Find the LCA of binary search tree. So finding out the LCA of a binary search tree, now here in this problem, let's say we want to find the lowest common ancestor of 0 and 5. Okay. So the lowest common ancestor of 0 and 5, okay, it would be a parent. Okay, like let's say somewhere it would be this, and this side it would be a lower value, this side it would be a higher value. So the lowest common ancestor of 0 and 5 would be like this, like it would hold up this property. Like if a node is a parent of two nodes, let's say, we know this is the left, okay, this would be the LCA and this would be the right. So left is 0, right is 5. So here, somewhere here, it would stand the LCA. We know that to be a parent. Now 0 and 5. So out of 0 and 5, we can see that like we came here, we would start from 6. So we know that this value is 6. So going on the right hand side, we would receive values more than 6. But more than 6 can never be our answer, because the LCA would stand in between of left and right. So we would go on the right hand side. Okay. Now we would check this. Is the value 0 and 5, this value is standing here or not? Yes, this value is standing here. Okay. So whenever we have a condition that the LCA is standing between the left and right, that is our answer. Let us verify this more with another example. Now let us try to find the LCA of 3 and 5. See, if you observe, 4 is standing in between. So LCA would always stand in between. So we came at 6. We know that if we move on the right hand side, we would have values more. So we are moving on the left hand side to get lower values. Then I got 2, which is not between 3 and 5, which is even less than, which is 2 is standing here and this is the range. But I want a range which is here. So to get a higher value, we need to go on right. To get a lower value, we need to go on left. So we need a higher value. That is why from this node 2, we would go to a higher value. Now at this point, again we have a condition which lies in between the left and right. Okay. So what is the code for finding out the lowest common ancestor? I can say that I would first have the minimum and max, because see, this is left, this is right. So if we have a value lying here, we would need to decrease the value. So I can say that if I can just take a max of LNR. If, let's say, this is max, max is equals to max of LNR. Let the maximum value out of LNR. Okay? So if we have a condition that the current value is greater than the root, then we would need to lower down the value. So we would go on the left hand side. If the current value is less than even the left of it, like the current value is standing here, then we need to increase the value to come at this side. So we would go on right. If the current value is standing between the left and right, then we would say this is the lowest common ancestor. So now let us first code the lowest common ancestor and then we would move to further explanation. So let us say that node star LCA, and then we have the node to the root, and then we have left, and then we have right. Okay. Now first we would find out the minimum. Minimum would be L and maximum would be R. But it can be switched like this. Like it doesn't really mean that left would always be less and right would always be more. That is why we are just segregating that. Okay. Or else, yes, minimum value. So here let us take this as capital L and capital R. That would make more sense. So lowercase l is equals to minimum of L and R, and lowercase r is equals to maximum of L and R. We have this condition. Now, till the root is not null, like we are not getting to the bottom, okay, we would keep doing this. What we are doing? We would say that if root dash data, if it is greater than R, if it is greater than R, what we would do? We would move to the left hand side. So root is equals to root dash left. Okay. Else if root dash data is less than L, then root is equals to root dash right. We would go to the right hand side. Else it is lying in between. If it is not on this side, if it is not on this side, that means it is in between, because there are three positions only. Either it would be, see, there are three positions only. Either it would be on this side, either it would be on this side, or either it would be here. So the last else condition would be on the middle. This is our answer. So we would return the value of root here. Okay. Else if we were not able to find any lowest common ancestor, then we would return a null value. This is the code of LCA. Now, when we have the code of LCA, okay, when we have the code of LCA, then the problem statement is different after we have the code of LCA. After we have the code of LCA, now the problem statement is print the path. Okay. So print the print all ancestors of the value x. Here, let's say for example, we have the value 4. How would we do it? It is comparatively easier. See, this is a binary search tree, so we would take full advantage of this. So we are here at 6. We are here at 6. So first we would print 6. We would go to the root, keep it. Then we know that here x is equals to 4, which is less than the current node. So less means what? Moving on the left hand side. So we would move on the left hand side. Again, print it. Okay. Now, after this, what we want? We want 4, which is greater than the current node. So it would be lying in which position? It would be lying, greater value would lie on the right hand side. So we would again go on the right hand side, print the value. If the value was 5, then we would have gotten down and we would have printed the value. Whenever we reach our end goal, we would return. So now the algorithm is pretty simple. We would say if the current node is greater than what we are searching for. Say 6 was greater than 4. Current node was greater than x. So move on the left hand side to get our goal. This is just like finding a node in a BST. If the current is less than x, then we would move on to the right. If we have reached, we don't want any more ancestors. If we go down 4, it would be a child of 4. It won't be ancestor of 4. So whenever current is equals to the value x, we would return so that we have all the ancestors of 4. Okay. Now let us code this up also. Print the path. Okay. In this print the path, I would call a function named as path. I would give it the root itself and then the node I want to target. Node star, let's say x. Okay. And I would have a vector passed by reference, that is an array list passed by reference, where I would save the path. Okay. So first we would push that. P dot push root dash data. And then we would decide if root dash data is greater than the value x dash data. Okay. Then I would say go to path. If root dash data is, if current is greater than data, then it would be root dash left. X would remain the same. P would also remain the same. Okay. Else if root dash data is less than x dash data, then what we would do is we would say path root dash right comma x comma p. Else in all other condition we would return from that point. Okay, we would return because we got the value. Going more deeper would just result in children's, not ancestor. We want all the ancestors list from the root to the bottom. Now, if you observe, the list we got was 6, 2, 4, 5. But if we walk up the ladder, it should be reversed. 5, 4, 2, 6. this is the proper hierarchy. So it just need to be reversed. So first we would find the LCA. Node star LCA. Node star LC, lowest common ancestor, is equals to LCA of root and then x comma y. After we got that LCA, we would pass it to the path. But before that, we need to make a vector of int, named it as p. Then we would just call the path root, and then this value would be LC, and this value would be p itself. After we got the path, we would reverse the path, p dot begin comma p dot end. After it is reversed, we would just check if p dot size is less than, like we have that much of, like let's say it is asking which is the fifth descendant, but we don't have 5 descendants. So if we have the bandwidth of the descendant, okay, if we have the bandwidth, but if the number of descendant is less than what is asked, we don't have the bandwidth, so we would return -1. If there is a bandwidth, we would return the kth one, because all the descendant would be stored in 0 indexed, so that is why we are just subtracting 1. Now let us see how many mistakes I am doing. I am writing the code in parts, so makes sense I would do some mistakes. This would be lowercase ln. I changed the occurrence of here also. Okay, this would be smaller case l and smaller case r. This would be the smaller case l and smaller case r. Yep. Let us see. P dot push root dash data. So what is the issue here? This is a vector and it has push back, not just push. Here I just wrote pass by reference. Okay, seems fine. Let's try to submit this. A lot of syntactical errors too, because I code in multiple languages and sometimes I'm not out of the zone of that previous language. That makes the small syntactical errors. Like I forgot like the variable names of like the syntactical mistakes which are language specific. So that's it. What is the time complexity? We are just drawing the line across the height, and the max number of nodes kept would be the max number of nodes in the height. That is why the space and the time complexity both is big O of h, and h being the height. That's it for today. Thank you and have a nice day.